Just a word about the exam. Okay, apart from the midterm, you should have already seen the two examples which are in my program page. Okay, there are two examples with the corresponding solutions of the two examples. The midterm test will be exactly in the same form. And so same number of questions, same questions for different graphs, of course. And the total possible score is 24. 14 is the score for being admitted to the oral part. Okay. If you fail or if you want to improve the score of the midterm, you can take it also after. The midterm will be, it's written anyway in my page, it's written, it is in December, I don't remember the time, anyway, the date anyway, it's written, you can find it there. But if you want to recover it, improve or recover after failing, then it's possible, and it will be during the written exams of my freshman, okay, in Geometry Algebra T. And if you want to recover, please write to me so that I can prepare a similar test for you, and so that I know that you are coming in that occasion. Okay, so please do, if you want, please write to me for booking. Okay, everything is anyway written in my web page. As for the oral part, I'll give you two titles which are either the title of a long chapter, typically graphs and subgraphs, or it will be vertex coloring, which is all planar graphs or directed graphs. These are long chapters, or the sum of two small chapters like this one. This is very short. It might be trees plus connectivity. Okay, so it might be choose between graph and subgraphs and trees plus connectivity. You choose one of the two titles and you write down whatever you remember of the chapter or chapters you have chosen. Okay, but it's not a written examination. It's just for you, for gathering your ideas without book. Okay, and then you come and we discuss what you have written, and if I have examples to ask you, if I have some proof to ask you, then I do. And if I have to say, well, this is wrong, how can you correct what you've written here, then you do, and so on. As you might know, as you surely know now already, we have quite a lot of scores, possible scores, from 18, which is the minimum for passing the exam, to 30 with honors, okay? And so there are various nuances of having a good exam, a positive exam, okay? All right. Pardon me? No, sorry. No need to book, because it will be during class, okay? And so you already should know. I should know because I've written it, but I don't remember. Anyway, it's written there when it is, so be sure to be here and for that date to be in class, and the midterm will be without booking. You need to book if you want to recover, because you will come in the occasion of a written proof, written test of my freshmen. Okay, and so while they do their test, you do yours if you have to recover the midterm. Everything is clear? Okay. So let's go on with some theorems of which you just have to know the statement, no proofs in this chapter. Next is this, that a graph with at least 3 vertices turns out to be 2 connected if and only if any 2 vertices of G are connected by at least 2 internally disjoint paths. What's the meaning of internally disjoint? It means for 2 paths having the same, they might have the same origin, the same terminus, or same origin and terminus, but no vertex in between, no internal vertex. Internal meaning, not the origin, not the terminus, should be in common between the 2 paths. And so this is a test, if you want, for knowing whether a graph is 2 connected, means at least 2 connected. Okay? If and only if any 2 vertices are connected by at least 2 internally disjoint paths. Okay. You just have to know that. No proof, as you can see. Corollary, if G is 2 connected, then any 2 vertices of G lie on a common cycle, which is built by putting together these 2 internally disjoint paths. Better said, one with the inverse of the other. Okay? And okay. And finally, this corollary, if G is a block with at least 3 vertices, then any 2 edges of G lie on a common cycle. That because of the lack of cut vertices in that block. Okay, that's all for this small chapter. Well, it's small, and it's even much smaller what I ask you to know, okay? So let's pass to this other chapter. This chapter is on two stories which are connected with playing things, so to say. The second one will be a commercial game, and the first one is something which was a puzzle which was debated in the pubs of a town in the 18th century. The town was Königsberg. Now it's in an enclave of the Russian Federation. It's Kaliningrad. And the town is, as you can see there, it is on 2 banks of the river Pregel and on 2 islands. And at that time, now there are more, but at that time there were these 7 bridges, okay, disposed in this way. And in the pubs, there was this puzzle. Everybody in Königsberg was talking about that. Is it possible to start from one place in Königsberg and to make a tour through every edge just once? Okay, so that you go through all bridges, but on every bridge just once. And nobody found such a solution, but they were smart enough to understand that if I don't find a solution, this does not necessarily mean that the solution is impossible. Okay? And this is frequent in graph theory, that you have a problem, you do not find a solution, and you wonder, is maybe a very strange solution possible which I don't see? And that's what they were thinking. And so not the mayor of Königsberg, but of Danzig, which is some 60 kilometers away, was also interested in that, and the mayor of Danzig had an idea to write into St. Petersburg to a very, very great mathematician, Leonhard Euler, okay, who was at that time working in St. Petersburg. And he wrote to Euler saying, there is this problem. Maybe it's a problem in that new type of geometry, which is called geometry of position of Leibniz. And Euler at the beginning answered in a rather rude way, saying, I don't see why you ask this mathematician. This is something of normal reasoning. Mathematics has nothing to do with this. But then the idea was running inside Euler's head, and he found actually an answer, which is a mathematical answer now, but it was the beginning of graph theory. He did not draw this graph here on the right. It was done in this way only much a long time after, in the 19th century. Okay, that they took again the same problem and simplified the situation in this way. So putting a vertex A for this island, a vertex B for that, a vertex C for that bank, and the vertex D for this bank, and then connecting them by edges like this, okay? Which makes things just a little bit simpler to look at. But Euler did the reasoning without this type of diagram, just reasoning on the map itself, okay? But now let's see what we can say in a formal way and in a general way. What do we say? What do we call a tour in a given graph G? A closed walk that traverses each edge of G at least once. And an Euler tour is a tour which traverses each edge exactly once. A closed Euler trail, okay? An Euler trail is a trail, not necessarily closed, that traverses every edge of G, okay? And so, what's the answer? Is it possible? When is it possible? And when is it not possible? And there is a very simple theorem. And again, when you see this, if and only if, this is a very strong theorem, meaning that your answer can be seen by examining something which is easy to check. Okay? Do you remember the characterization of bipartite graphs? You know what a bipartite graph, if there is a bipartition and so on and so. But there is this necessary and sufficient condition. A graph is bipartite if and only if it contains no odd cycles. So if you can check all cycles and see that none is odd, then you can deduce that the graph is bipartite. Conversely, if you find at least one odd cycle, you can say, no, there is no possible bipartition. Okay? And here, what's this necessary and sufficient condition? An unempty connected graph is Eulerian, meaning that it has an Euler tour, a closed Euler trail, if and only if it has no vertices of odd degree. Okay, so this is it's easy to check. You visit every vertex, count the number of edges incident to that vertex, that's the degree. Even, you get to the end, all of them have even degree, then you're sure that an Euler tour exists. How to find it? We'll talk about that later. But then you have this thing, that an Euler tour is possible. How do you do it? Just by thinking that whenever you enter you start the tour at any vertex. And then you enter another vertex. And since the degree is even, then surely there is at least one edge to go out, for going out of that vertex, okay? And you can delete the edges you are going through, but always you are left, since you delete 2 each time, you always are left with an even number of edges. So whenever you enter a vertex, you are sure that you will be able to get out. This is the intuitive idea of this proof, okay? Again, one way one implication is easy, and the other is a bit less easy than that, okay? But the main idea is actually this. Instead, a connected graph has an Euler trail if and only if it has at most 2 vertices of odd degree. So, if you have 2 vertices of odd degree, you can start on one, and there is a trail which goes through every edge just once and ends at the other vertex of odd degree. Okay? So we have just a very, very simple condition, okay? And you can use this for these children puzzles. Which of the following figures can be drawn without lifting one's pen from the paper or covering a line more than once, okay? And so you can know that by seeing what are the degrees of these vertices. Here I have vertices of degree 2, here degree 4, 4, 4, 4, 4, 4, 1 and 1. So the theorem tells us that there is no Euler tour, but there is an Euler trail starting, say, from this and ending here. Okay, or conversely starting here and ending there. Here it's not possible because of this vertex of degree 3, that other of degree 3, and degree 1. And so it's not possible to have even an Euler trail. If you just delete this edge here, then you're left with just 2 vertices of odd degree, this and this, and then again you have an Euler trail starting from here and ending here, or conversely. Well, what about here? Again, you just have to check the degrees, and you find here a degree 5, here a degree 5. All other degrees are odd, and so again, you should be able to find an Euler trail from this to this, or conversely. Okay? It's a good thing to try by yourself without knowing a rule. We'll see Fleury's algorithm, which will tell us how to solve the problem of finding a trail when it's possible, okay, or an Euler tour when it's possible. If possible, and that's very nice, and I think you find it amusing. If possible, draw a Eulerian graph G with ni even and epsilon odd. Okay? Otherwise, explain why there is no such graph. And the authors do not tell you what the situation. Is it possible? Is it not possible? If it's not possible, tell why, say why. And if it's possible, draw it. Tell me.
Eulerian graph should follow the Eulerian curve. And in Eulerian curve, the number of edges are exactly the same as number of vertices.
No. You can see that here. Take this away. Take this away. Or This is Eulerian. You have that every degree is even, but this does not mean that every degree is 2. Okay? So this is the Eulerian, and it's rather easy to see a tour here. Okay, 1, 2, 3, 4, 5, 6, 7. So I've done a whole tour. Okay, but you do not have the same numbers of vertices and vertices. But it's nice. You have an idea, there is a counterexample. Okay, now you tune yourself to this new notion. You can think of it. But I don't give you the answer. But try that. Okay? And now, what did I tell you? When you have a nice thing in terms of edges, why not try the same idea but in terms of vertices? And that's what Sir Rowan Hamilton, the great researcher in mechanics, okay. He had a friend who wanted, his friend Grace, who asked him to invent a game for commercial use. And I think he got some money out of that, okay? And so he devised that. He took this graph, which is the graph of the edges of the dodecahedron, and the idea was to find a cycle touching every vertex exactly once. Okay, I don't know how it was played by 2 people. Anyway, the idea was that, and so now we call a Hamilton cycle, if it exists, a cycle which contains every vertex of G. A Hamilton path is a path containing every vertex. Okay, so with no repetition. A Hamilton cycle with repetition only of origin and terminus, which must be equal. Okay, and so it's very similar. You might think, well, okay, maybe it's a small variation from Euler's theorem. Absolutely not. This is a totally different problem. And I can tell you that so far there is no good necessary and sufficient condition. We will see one, but which is not so good. It is absolutely not like the one we had just seen for Eulerian graphs. Okay, something for which you can visit all vertices and check even degree, even degree, even degree. Okay, so an Euler tour exists. There is nothing like that you can do by visiting edges, by visiting vertices, and so that you can at the end say, okay, then a Hamilton cycle exists. We don't have so far such a theorem. Okay, we have some interesting necessary or sufficient condition, also one which is necessary and sufficient, but you'll see is not so good. Let's see. Here we'll also have a small proof, not of this anyway. Theorem. If G is Hamiltonian, what's a Hamiltonian graph? One in which Hamilton cycle exists. If G is Hamiltonian, then for every non-empty proper subset V of S of V, we have that the number of components of G minus S is less than or equal to, when we have this, it means cardinality, number of elements. Okay, so if, but mind, it is a one-way implication. If G is Hamiltonian, then for every non-empty proper subset, S of V, omega of G minus S, that is the number of components of G to which you have taken away the subset S of vertices and all incident edges, is less than or equal to the number of elements in S itself. Okay? How can you use such implications which go just one way? Often you can use them by the counterpositive or counternominal. Has anybody never heard what the counterpositive of an implication is? You never heard? Okay. So I explain this because it's very, again, as mathematical methods and not just graph theory, it's very important to know that we make count on the counternominal or counterpositive of an implication. An implication written like this: A implies B, where these are propositions, okay? Assertions about something, okay? This is defined as equivalent to not A or B. Okay? That's not a very nice thing for normal, the normal intuition. I don't want to talk very much about the sense of the implication in mathematical logic. But please remember that it is defined by a truth table, and the truth table of the implication is exactly the one of non-A or B. Okay? Now, one terrible and very common mistake is to think that A implies B is the same or is equivalent to its inverse, which is B implies A. Absolutely false in general. What can I be sure of if I have A implies B? If A implies B is true, then also its counterpositive which is not B implies not A, sorry, is true. Let's see why. What's the meaning? In fact, what's the meaning of not B implies not A? This is equivalent to, it is not B or not A. Okay? which is equivalent to not B is equivalent to B. So B or not A equivalent to O or is commutative. So the truth table of D or E is the same truth table of E or D, and so this is equivalent to not A or B, that is A implies B. Okay? And so when you have such an implication, you scarcely can use it for confirming something. Meaning that if you find that for a certain graph G, you take away in all possible ways a set S of vertices, and you find that this inequality holds, you have nothing in your hands. Okay? Maybe it is Hamiltonian, but who knows? On the contrary, if you find that for a particular subset S, if you take it away, then the number of components you get is greater than the number of elements you are taking away, then it surely does not, it is not Hamiltonian. Okay? So implications which are just one way are useful for checking that something does not occur. Okay? Let me take this example out of what I teach my freshmen. You may remember the notion of two square matrices being similar. I don't want you to think of it, but you might remember that there is the notion of a matrix A is similar to matrix B, and then the notion of determinant of a matrix. Then we have this implication. If A is similar to B, then the determinant of A is equal to the determinant of B. If you have two matrices and you find that the two determinants are equal, you have nothing in your hands. Maybe they are similar, but maybe not. On the contrary, if you see that the two matrices have different determinants, then you're totally sure that the two matrices are not similar. You are using the counterpositive, and it gives you something. A negative answer, okay. Also here, you can get a negative answer. You find, for instance, something. Now I draw something very easy to see that it's not Hamiltonian. Okay. Okay, take this graph. Of course, it's not Hamiltonian because once you pass here, you can only either go from left to right and then you cannot come back, or you stay on the left-hand side and you cannot reach the vertices on the right. Okay, if you have a cut vertex, surely it's not a Hamiltonian graph. Okay, but here you can see it also by that rule, because if you take S, this is vertex V, and if S equals the set just containing V, then what happens if you delete S, that is, if you delete V, you get that the number of components you get is greater than the number of elements you are deleting, okay? And so here is a very simple application of the counterpositive of this condition, okay? And all right. also you have this, and for today it will be the last thing I do, because I also give you a rather strange proof of this. If this is a simple graph with at least 3 vertices, and small delta is greater than or equal to half the number of vertices, then G is Hamiltonian. This time we have that being Hamiltonian is the B of the situation, okay? And let's see, by contradiction, suppose that the theorem is false, and let G be a maximal non-Hamiltonian simple graph. What does it mean, a maximal non-Hamiltonian simple graph? Of course, you understand that it's easier to try to answer intuitively to this. With the same set of vertices, is it easier to have a Hamiltonian cycle if you have quite a lot of edges, or if you have only few edges? Reasonably enough, if you have quite a lot of edges, okay? Because you might try in more ways, okay? And, okay, the idea of maximal non-Hamiltonian simple graph is this. So, let's think that you have a non-Hamiltonian simple graph with at least 3 vertices, and with this condition that small delta is greater than or equal to n divided by 2, and that it's maximal for being non-Hamiltonian. Meaning, if you have even a single edge, then a Hamiltonian cycle comes in, okay? So maximality is very important in proofs, in many proofs of graph theory. Okay. So now let U and V be non-adjacent vertices, vertices which are not the ends of the same edge. Then, by this choice of maximality of being non-Hamiltonian, if you had even a single edge, then you get a Hamiltonian graph. Add this edge UV, okay? Then, the difference is between G, which is non-Hamiltonian, and G plus UV, which is Hamiltonian, means that every Hamiltonian cycle must contain edge UV, okay? All right, then there is a Hamilton path V1, V2, Vn with origin U equal to V1 and terminus V, which is Vn, a Hamilton path, okay? So a Hamilton cycle you have because edge UV closes a Hamilton cycle. So you have a Hamilton path starting in U and ending in V. All right? Now you build this. You build these two sets, which are a bit strange. You build a set S, which is such that it is built by these vertices Vi, such that U Vi plus 1, so from U to not Vi itself, but the one which follows in this Hamilton path is an edge of the graph. And T is the set of vertices which are connected, which are adjacent to V. Okay? Two different ways of constructing the thing. Vi is in S, not if it is connected to U, but if the following one in the path is connected to U, okay, is adjacent to U. In T you have that Vi is in T if itself it is adjacent to V, okay? Now what we have is that Vn itself, that is V, is not in the union, okay? Why? Because there is no following vertex which in the path meaning since V is the last one, there is not a subsequent vertex in the path. So V itself does not belong to S, and V itself is not adjacent to itself. There is not a loop. Okay? We are talking about a simple graph. So at least V is missing from the union of S and T, and the number of elements in S union T is less than Ni, because at least V is not belonging. Actually, only it is not belonging. Now there is a reasoning by which you can see that S intersection T is the empty set. Let's see why. Assume that there is a vertex Vi in S intersection T. So a vertex Vi like this, such that the subsequent one in the path is adjacent to V1 and itself is adjacent to Vini. Okay? Assume that such a situation occurs, so that Vi belongs to both. Then what happens is that you could have a Hamilton, you would have a Hamilton cycle like this. V1, V2, you go up to Vi, you jump to Vini because Vi is adjacent to Vini. You come back like this, you get to Vi plus 1, and then you jump to V1. Why? Because Vi being in S, Vi minus I plus 1 is adjacent to V1. So you would close a Hamiltonian cycle, but remember that we are here in G, where no Hamiltonian cycle exists. So this means that it's not possible that there is a vertex in the intersection. So the intersection is empty, and the number of elements in the intersection is 0. Now there is this fact that you have what is called the inclusion-exclusion property. Let me see how to show it to you. I take the three of you. Can you please show your face to all of them? Take the set of the three. No, please leave the spectacles, the glasses. Now I can have two sets. A set S of people with glasses and set B of female people. Okay? And so I can build the union, which is the three of them. If I want to count, I can say, well, the union, so I take the number of women, which is 2, the number of people with glasses, which is 2, 2 plus 2 is 4, but it's not true that it's 4. What should I do? Use the inclusion-exclusion principle. So the number of elements of the union is the sum of the number of elements of the two sets minus the number of elements in the intersection, which is the lady. Okay? And so, if you want to have, the formula is this. Number of elements, cardinality, let's call it as it is, cardinality of S plus cardinality of T equals cardinality of the sum plus cardinality of the intersection. Or if you prefer, cardinality of the union is sum of the two cardinalities minus the cardinality of the intersection. This is called the inclusion-exclusion principle. Okay? And now, so we can have this. We can also say that if you take the degree of U, it is the number of elements in S by the definition of S. The degree of V is the number of elements in T by the definition of T. Okay? But what you have is that, so this sum is the union of these, is the sum of these two, which is the number of elements in the union plus the number of elements in the intersection. This number of elements in the intersection, I've just shown that it's 0, and before we have seen that V is not belonging to the union, so this is less than ni, strictly less than ni, and so it's impossible that small delta is at least greater than or equal to ni divided by 2. Okay, and so you see that the hypothesis is false if you assume that the thesis is false. And so this means that necessarily the theorem holds. If G is a simple graph with at least 3 vertices and a small delta is greater than or equal to ni divided by 2, then surely G is Hamiltonian. This time we have something implying the being a Hamiltonian. Before we have, if G is Hamiltonian, then this happens. Now we have, if that happens, then G is Hamiltonian. Next, in next lecture, we'll see a not so satisfactory if and only if, necessary and sufficient condition. Okay, that's all for today. Ciao.